Okay, so shall we start teaching now? Okay, we are continuing chapter 4. We talked about the polarization a little bit. Okay, so I'm gonna list the topics I wanna talk about today, and then we go by that. So we are in chapter 4.
Professor, you might want to check your focus. Oh, there it is. It's back. Sorry.
Yeah, you know what? Sometimes I put a little star here. Okay, and this keeps the camera in focus. It's interesting because this is so white and clean. Sometimes it doesn't know where to focus. So polarization, the field of a polarized object bound charges, and then the electric displacement. All right, so these are the topics we are covering from chapter 4 today. So chapter 4 is all about putting a dielectric, non-conductive material in an electric field and see what happens, okay? We look at that in a few different perspectives. Let's imagine you have the electric field E naught here, and you put this object, which is dielectric, like plastic or something like that, non-conductive, inside the electric field. So what you get, is that the molecules or atoms in this material gets polarized, okay? So from a completely neutral, non-polarized material, suddenly it becomes a polarized material, okay? So you can imagine now this material is made of millions and millions of small dipoles, okay? Many small dipoles, okay? So we have a polarization here inside the material, okay? So the way we quantify that polarization is this. Let's imagine you pick up a small volume from this, okay? And then a small volume in this, let's say d tau, as a whole now carries a dipole moment, okay, because it's made of many dipoles, okay? So the way we quantify that polarization is that we assign for this area, this volume, we say the dipole moment is P, this vector that I'm going to define in a bit, times the volume, okay? And this P is called polarization. So basically, the polarization is a dipole moment that you can find in a specific volume, a small volume, divided by the volume. So it's polarization, sorry, dipole moments divided by volume, or dipole moment per volume. Okay, so any material, if you put it in an electric field, you will get polarization, and the polarization is defined by dipole moment of any small volume. You can find the material divided by volume, or dipole moment per volume. Okay, so this is what happened. And the next thing we're going to look at in later sections is that we want to say, if we have electric field E0, we put the material here, we get polarization of P because of this, then what is the electric field inside that material? Okay, so you can imagine it's going to be a bit complicated because inside we have, of course, E0, the electric field that was there otherwise, plus the electric field created by these little dipole moments. Okay, so you have two effects combined. Okay, so we're gonna look at that when we talk about the electric displacement. Okay, so first, let's look at what kind of electric field the polarization can create. Okay, now for a moment, let's forget about the electric field outside. Okay, just imagine we have one dipole, and for whatever reason, just imagine we have one piece of the dielectric material, and for whatever reason, this material is polarized. Okay, and that means this material is made of many, many little dipoles. Okay, and for that, we quantify P, the polarization, and now we want to see what kind of electric field is created by such polarized material. Okay, so to do that, we're gonna go back to the dipoles, okay, and we're gonna look at what kind of the electric potential and electric field was created by the dipole. Okay, we look at the dipoles in chapter 3, and we know that if we have one single dipole with polarization of P, okay, with dipole moment of P, if we have that, the potential created by this dipole is 1 over 4 pi epsilon 0 dipole moment dot distance vector divided by distance to the power of 2. Okay, so this is the kind of potential you get from one single dipole. Okay, now imagine we have this piece of material which is big and is made of many, many dipoles. What should we do? We should integrate this to calculate what electric potential is created by the whole volume in this material. That means we should integrate V dot R. The constant 1 over 4 pi epsilon 0 is always there. And this term we should integrate. Okay, so here I said every small infinitesimal volume has the dipole moment of this. Okay, so this dipole moment should be kind of replaced with dipole moment here we get from one single dipole. Okay, so I'm going to write 1 over 4 pi epsilon 0, and I'm going to integrate here now P, which is polarization. Okay, so one of them is capital P, the other one is small. So let me put this line here so that you see this is capital and this is small. Okay, so this is polarization dot d tau, okay, which is a vector, and the whole thing should be dot product times r hat, okay, divided by r squared. And this integral runs over the volume of the polarized dielectric material that we have. So this becomes technically the integral that we can calculate electric potential, and subsequently we can calculate electric field created by a polarized object. Okay, remember, this is not specifically a charge distribution. There is no net charge here. This is just atoms and molecules in a non-conductive material that are polarized, means all the dipoles, many of the dipoles are aligned in the same direction in a way that you can assign a polarization to this. Okay, so again, here let's forget whatever we have from outside. Okay, perhaps there was an electric field that made everything polarized, but let's forget about that. We are just now focused on the electric field created by the polarized dielectric. Sounds good? Any questions so far? Is it clear what geometry, what specific thing we have and what we are looking at?
Which one was the small p?
The small p was dipole moment of a dielectric. So this is dipole. So this is a dipole moment. Okay, and the rest are polarization. And for the rest of the class, I'm gonna work with polarization. So except this single one, every P that you see today is polarization, not the dipole moment.
Can you explain the dipole moment again, just to clarify?
Okay, dipole moment is when you have a dipole plus, minus, one single dipole if you have, okay? So there's a dipole moment you can assign to this, which is Q, the charge here, times D, the distance from negative to positive, okay? So this is the dipole moment. If you have one single dipole, you can assign the dipole moment, And the potential created by this can be calculated based on this equation, which is dipole moment right here. Okay, so we start from here and we make the assumption that the polarized dielectric is made of many, many dipoles. So that's why we are integrating the potential of a dipole here over the whole volume of the dielectric material.
Got it.
Okay, so to make things a little clear and to create more space, I'm gonna get rid of this and also the whole equation here. And I'm gonna rewrite this up here because I want to expand this. So this is my starting point. 1 over 4 pi epsilon 0 integral over the volume of this dielectric material. Here I want to rearrange it and write it in a better way. I want to write P polarization dot r hat divided by distance vector square d thou. Okay, so this is exactly the same thing. I just rearranged and put d thou after the fraction. This looks a lot better. Okay, so I'm going to start from this. Okay, so now I can change a little bit. And what I'm doing for the next couple of lines is only some mathematical tricks. Okay, so I'm going to separate r hat by r square. Okay, so the part of the fraction that I put in red dotted circle, I'm going to say that r hat divided by r square, I want to write that in terms of gradient of 1 over r. Okay, so this is technically gradient of 1 over r. So now here inside the integral, we are running over the dielectric material. So this is different from the r outside. Let's use the prime coordinate here. Okay, so I want to make it d thou prime, and the prime coordinate runs over the dielectric material. For that reason, I'm going to make this gradient prime as well, so that it reflects its gradient with respect to the coordinates that runs over the dielectric material. Okay, now with doing that, I'm changing this integral. Looks a little more complicated, but eventually you will see that that's really helpful. 4 pi epsilon 0 integral runs over the same volume that we are getting now. P dot gradient in the prime coordinate 1 over r times d thou prime. Okay, now because we have the gradient here, we can use the integration by part and make this in the form of two different integrals. Okay, so here I want to say we do integration by part. Okay, and then v of r is 1 over 4 pi epsilon 0. And then we get two integrals. One of them, of course, both of them are on the same volume V. One of them is the divergence in prime coordinate of P over R d thou prime. The other one is the integral of 1 over R divergence of P d thou prime. Okay, so using integration by part, I made it to two integrals. Okay, one of them has a divergence of P over R, the other one has 1 over R. By the way, this should be the distance R, 1 over R divergence of P. Okay, so now if you look at the first integral, this is divergence of a function over the whole volume. Okay, so if we use the divergence theorem, we can change this, okay, divergence, integral of divergence over volume, we can change that to the integral over the surface of the volume, okay? So this integral, I'm going to draw the bracket again, this integral can be change to a surface integral, which is a closed surface, and that is over the surface of the dielectric, okay, of the not the divergence but this function itself. So this can be written in terms of the integral of 1 over r times p dot dA. And dA is the element on the surface. The integral again runs on the surface of the dielectric, so this is a surface that encapsulates this volume here. Okay, so I use the divergence theorem to make this change, and I'm going to write the second integral the same way that it was. 1 over r divergence of, so this is not p prime, this is p theta. And of course, we have 1 over 4 pi epsilon 0. And then we have VR here. Okay. So I did these changes. I started from here. Here, I used the gradient of 1 over r. I made it this integral, which it doesn't look easier than this, but it helped me use integration by part and separate these two. Okay. And there's a reason I did all these things and moved from this simple looking to this rather more messy looking integral. Okay. The reason is that if you look at the terms here, they have very specific physical meaning. Okay. If you remember, any potential created by a surface charge, okay, if you remember, if you have a shell, okay, with surface charge density, if you wanted to calculate the integral, sorry, if you wanted to calculate the potential created by this, we could integrate and the integral would have looked something like this. 1 over 4 pi epsilon 0 integral of sigma over r times dA, right? So this is usually the potential created by a surface charge density, okay? And if it's closed surface, you can close it and it's gonna be on the surface, okay? So this is what we had from the very basic potential topic that we talked in chapter 2, I guess, right? Now, if you compare this integral with the one we have here, the first term, it has very similar shape. We have 1 over 4 pi epsilon 0 times here we have sigma over r dA, here we have 1 over r p dot dA, okay? So the mathematical form of the first term is in fact very similar to the case that you are calculating potential created by surface charge, not necessarily polarization. And that surface charge is, I'm going to say here, define that as sigma b being equal to p dot dA. Okay, so the first term, again, looks like a potential created by a surface charge, where the surface charge sigma b is p polarization dot dA. Okay, so mathematically these are equivalent to each other. If we look at the second term, okay, now we have 1 over 4 pi epsilon 0, an integral that runs over a volume, 1 over r divergence of p. The second integral looks like the potential created by a volume charge density. Again, to remind you, if we have volume charge density, okay, so let me modify this a little bit. If you have a volume in which you have rho volume charge density, the integral that calculates the potential is something like this. 1 over 4 pi epsilon 0 rho times d thou. Okay, so this is how you calculate potential from a volume charge density. And now if you look at this, of course, the integral is over the volume, not surface, right? So V. And now if you look at this, okay, this has very similar shape as this equation, with the difference that the volume charge density should be negative of the divergence of P. Okay, so going back again, the potential created by a polarized object has the form like this, and that is similar to the potential created by a volume that has volume charge density and surface charge density, defined as sigma b surface charge density being p dot dA and volume charge density being negative divergence of P. Okay, so mathematically we started here and we came to this conclusion. Okay, so what I'm going to do next, I'm going to explain like physically what does that mean. Okay, and that gives you a bit of insight of how polarization can create electric potential and electric field. Okay, so for that I'm going to get rid of everything here in the middle up to here. Okay, and then draw a few more graphs. Okay, so here is what we have initially. We have a dielectric material which is polarized. Okay, so I want to say if we want to calculate electric potential and electric field created by that, we can now consider a very similar volume and shape. Okay, of course, it's not that similar, but let me try to do something better. Okay, anyways. So imagine this shape has very similar shape to this. Instead of considering it's made of all these little dipoles, I want to consider it's made of something that carries an actual volume charge, and on the surface carries an actual surface charge as well. Okay, how much volume charge? I want to say that rho, I'm going to call it rho B. You will see why I'm calling it like that in a minute. I'm going to say rho B should be negative of divergence of P. Okay, so what is P? P is polarization of the material on the top. Rho B is the volume charge density here, which is defined as negative of divergence of P. Okay, and then we have surface charge, sigma B, and I define it as P dot dA. Okay, that means, sorry, not P dot dA, but P dot n hat, where n hat is the unit vector perpendicular to the surface. Okay, P dot n hat. Okay, so I define sigma B, the surface charge, as P dot n hat. Okay, now, if you consider these two, these are two physically different things. One of them has volume charge, the other one has polarization. The other one of them has surface charge, the other one has only polarization, okay? But with this mathematical step that we took, the potential and the electric field created by the second one is going to be exactly the same potential and electric field created by the first one, okay? So that means if you have a polarized object, okay, in order to calculate the electric field, you don't need to go through the hassle of calculating potential created by all these little dipoles. You can make the assumption that you have something different, physically different, but carries some volume charge and surface charge. The potential created by the second one eventually is going to be exactly the first one, okay? So this is what we did through first some mathematical steps, and then we looked at the form of the integrals here, and we figured that these form of the integrals are very similar to the surface and volume integral when we calculate potential. Okay, so from here to here, it's hard to do it like from physical intuition. We did some mathematics, but eventually we can explain it in terms of what physical object we have, the actual thing we have, and the second thing that is different, but it's going to give us the potential and electric field that we would have calculated from the first one. Sounds good? Is it more or less clear, the steps we are taking here? Okay, good. Any question? All right, so let me see if I can do one example, okay, and I'm going to explain more on how this volume charge and surface charge are related to the polarization, okay? Cool. So let me clear this one. So just to give you one example, I'm going to do example 4.2. Okay, and this is a system that we have polarization, but from the polarization we want to find the surface and volume charges and relate that to one of the examples that we did previously. Okay, so example 4.2 says that we have a sphere which carries uniform. Oh my God. Okay, it says that we have a sphere which carries uniform polarization P. Okay, that means this sphere is a dielectric material and somehow it's polarized in a way that it has uniform polarization P everywhere. P is, let's say, pointing up. Okay, so anywhere on the inside this sphere we have this polarization. Sounds good? Now the question is what electric field and electric potential is created by this polarized object. Okay, so again, one way is we make the assumption that this material is made of many, many little dipoles. We can integrate the electric potential of the dipoles, which is 1 over 4 pi epsilon 0, and then we do P, the polarization dot r hat over r square d phi prime, and this integral runs over the volume V of the sphere. Okay, so this is one way, but it's not easy. Okay, so instead of that, what I'm going to do is that I want to say this is equal to the integral of 1 over 4 pi epsilon 0. I'm going to use two integrals, one of them surface, the other one is volume integral, and I want to use the density of volume charge and surface charge the way we calculated based on this. Okay, so I want to make an assumption that instead of integrating the dipoles on this, I want to consider a separate system which carries some volume charge, rho b, and carries surface charge, sigma b, in a way that rho b is negative of the divergence of P. In this case, P is a uniform vector pointing up. Okay, so divergence of that becomes 0. So eventually, the rho b is 0. And sigma b is P dot n hat. And if P is uniform everywhere, n hat is a vector perpendicular to the surface, P dot n hat becomes equal to the magnitude of P dot cosine theta, where theta is the polar angle here. Okay, so I want to calculate potential created by non-polarized system of carrying rho b and sigma b, and that's going to do the actual thing that I was looking for. Okay, so I'm going to, instead of this, I'm going to say this is complicated, but this is the right one. And not that it's not correct, it's just complicated. I want to do this integral over surface sigma b r d a plus integral over volume rho b over r d tau, and closed. Okay, so this is just different view of a polarized object. Okay, instead of looking it as something created by many, many dipoles, you can look at that as it's carrying certain volume charge and surface charge. Okay, so now if you look at this, the surface charge density is created by this, created by the polarization is something like this. This is very similar to the one of the examples we had for separation of variable in a spherical coordinate, that we have a surface charge density which is proportional to cosine of theta on a surface, on a shell, on the surface of a sphere, and that's going only on the surface and nothing in the middle. Okay, so I don't want to do the details of this, okay, as in your textbook, I'm just gonna refer this charge distribution and potential created by this charge distribution to one of the examples in chapter 3. Okay, I don't remember what example was that, but there was one example in chapter 3 that calculated electric potential created by a surface charge proportional to cosine of theta. The potential as a function of r and theta inside and outside have the form of this. For inside the sphere, it was P over 3 epsilon 0 r cosine theta, and the potential outside was P over 3 epsilon 0 r3 r2 cosine theta. Okay, so different terms for inside and outside. Okay, and this is the potential we get, and of course from the potential we can calculate electric field. Okay, inside the r cosine theta is in fact equal to z in Cartesian coordinates. Okay, so inside the sphere we have P over 3 pi epsilon 0 times z, which is not uniform but linear with respect to z. If you take derivative of this to calculate electric field, that becomes a constant field. Okay, and if you look at the outside, the potential has a very similar form as the potential created by dipole. Okay, so this potential outside the sphere, you can write it in terms of the potential created by the dipole, 4 pi epsilon 0, dipole moment of P r, I'm going to call that, dot r hat over r square. Okay, so these two are very similar to each other with the definition that the dipole moment being 4 over 3 pi r3 times the polarization. Okay, so again, the basic idea is this. You have a material which is polarized, okay, and in order to calculate potential and electric field, instead of going through every single polarization and integrating the potential created by dipoles, okay, which is difficult, okay, you make the assumption that the material is made of something that has surface charge, okay, you integrate the surface charge and volume charge, okay, and the way you calculate the surface charge and volume charge, these are called bound charges, okay. What you do is that you look at the divergence of P to calculate volume charge, and you look at P dot dn on the surface to calculate the surface charge. For this specific example, the P polarization was a uniform vector, so the divergence of P is 0, the volume charge becomes 0, but surface charge is non-zero and is proportional to cosine of theta, the polar angle in spherical coordinates, okay? And this makes the whole system very similar to the one of the examples we did in chapter 3, okay? And this is the kind of potential we get out of that, okay? Something interesting is that potential inside is linear with respect to z. That means that creates a constant electric field inside, okay, constant and uniform electric field inside. And for outside the sphere, if you look at the terms for the potential, this is very similar to the potential created by dipole, okay? So you can assume that the potential we have is created by dipole, and the dipole moment is related to the polarization of the object with this equation, okay? So this is only the shape of the potential, and of course it's going to be the shape of the electric field outside, which is very similar to what is created by dipole. Okay, so if you want to sketch the electric field and electric potential, inside the electric field is uniform, like this. Okay, and it's going to be something like this. Okay, and outside, you're going to get terms like this. Okay, this is the kind of electric field lines you're gonna get. Inside, something completely uniform. Outside, similar to what you would have get from a single dipole.
Professor, for the when you define the P of R, what is the capital R? Does it have an exponent?
Oh, the capital R, sorry, I should have mentioned. The capital R is the radius of the sphere.
So is it just R when you
It's a
define?
constant.
Okay.
Capital R is a constant. So inside, outside, you just separate by R. Again, from here to here, I skipped many parts, of course, but that's covered in one of the previous examples. Okay, so from here to here, many parts are skipped.
Wait, I think, Victor, were you talking about that PR equals 4/3 pi r
Yeah.
cubed exponent? Yeah, I think that's a cube because it's the sphere.
Okay. Thank you. Thank you.
I do have a question.
Sure.
So when you did integration by parts, you were able to bring an integral from a volume integral to a surface integral.
Not at that step. When I did integration by part, I had one term that had divergence of P over R. Okay, and using the divergence theorem, I made that volume integral the surface integral.
Okay.
Is it the answer to your question?
Yes.
So I did two parts. One of them integration by part, and next part I used divergence theorem to make the volume integral surface integral.
Okay. Okay.
Sounds good?
Thank you.
Okay. Okay, so what I want to do next is that I want to again discuss why we can do this transformation. From a polarized object made of dipoles, I'm creating another object that has volume, surface, volume charge, and surface charge. Okay, so I want to again discuss what does it mean in terms of the physical charge distribution that we have. Okay, so hopefully that's going to help you developing intuition towards why that even works. Okay, so let me clear this. Okay, so let's consider we have some cylindrical shape dielectric. Okay, and for the sake of argument, let's imagine I cut this part like this. Okay, shape like this, and imagine it has for now a uniform polarization in this direction. Okay, so P polarization is in this direction. Okay, and that means this piece of the cylinder is made of dipoles all pointing this way. Okay. Now, if we go back to my previous discussion, in order to calculate electric field of this, I would look at a volume charge density being divergence of P and a surface charge density being P dot N. Okay. That means on this surface that P is here, that N is in this direction, we are assigning some negative charge to the surface. Okay, and in this direction, that N is in this direction, we are assigning some positive charges to this. Okay, and in a way that because of the angle here, the surface charge density on this side is lower than this side. Okay. So for now, let's consider P is uniform, okay? And I'm gonna argue why these two should create exactly the same electric field and potential, okay? So for that, let's just consider really positive and negative charges over the whole volume, okay? When we say we have many, many little dipoles, that means we have many, many small negative and positive charges here, okay? If you look at inside the volume, I'm gonna reproduce that here, and I want to exaggerate the size of the dipoles for the sake of the argument, okay? So imagine you have negative charge and positive charge here, and this is one dipole, right? And if you continue this, there are another dipole, negative charge and positive charge, and negative charge and positive charge here, okay? So if you consider one piece right in the middle, okay, what you have this accumulation of negative and positive charges in a way that these charges cancel out each other, okay? For each positive charge, there's negative charge sitting next to it, and that really cancels out the net charge inside, okay? Now imagine you move all the way to the surface, okay? So what do you have on the surface? You have these aligned, polarized, negative and positive charges that come all the way to the surface. So when you come here, you always see the positive charge, which is half of a dipole, okay? Because they align on that side, you see a lot of positive charges. And after that positive charge, there's no negative charge because this is the surface, right? So because of that, you get some accumulation of positive charges here, okay? And if you look at this side, again, what you see is the negative side of the dipoles on the surface. Of course, there's positive charge next to it, but right on the surface, you have this accumulation of negative charges, okay? So these are the dipoles you have, okay? So as a whole, if you look at the system, inside you have negative and positive charges just canceling out each other. They don't create any net positive or net negative charge distribution, volume charge distribution in the middle. But when you come on the surface, you see one tail of the dipoles. If you look from this side, you see the negative tails of the dipole. If you look at the other side, you see the positive tail of the dipoles. And that's why when we say P dot N on this side, it creates a negative surface charge on this side and negative and positive surface charge on this side. And that's why with only considering surface charges, you can capture the potential we have created by all these dipoles. Is it clear? No? Any question?
No, no question.
Sure. No question? Okay. So anyway, so this is for a case that we have uniform charge density. Okay, so if the uniform polarization, if the polarization is not uniform in a way it has a divergence, that means the dipoles are converging or diverging from one point. Okay, so a diverging case is something like this. You have P, okay, I'm just exaggerating the case that it's really diverging from one point. And if you have diverging polarization, means you have dipole moments diverging from one point like this. Okay, so if you look at this, and if you try to imagine positive and negative charges that are creating this dipole, and if you want to look at the geometrical localization of those, what you see is something like this. Negative charges here, and positive charges are outside. Okay, so this is basically a dipole situation that these dipoles are diverging from one point. Okay, so if you have divergence like this, you will see the charge of the same sign kind of accumulated in the middle, right? So if you have diverging points, diverging electric field, in one part of the space, you can have accumulation of either positive or negative charges, okay? And that's how a volume charge density can be related to the divergence of the polarization, okay? So if they are diverging like this, the polarization is positive, and with this negative sign, you can assign the negative volume charge density to right in the middle of this because you have accumulation of negative charges, okay? Of course, if you change the sign and you change the direction of the polarization, you have converging polarization. And if you look at that, a converging polarization is going to give you some positive charges, okay? So these volume and surface charge are something that can be interpreted based on how the positive and negative charge, how positive and negative charges of the dipoles are distributed and localized in a space in a way that they can lead and create a specific surface charge or a specific volume charge densities. Okay? So I hope that you can read the textbook and watch maybe this video again, and the concept becomes more or less clear for you. Sounds good? Any question? Okay, so we covered polarization, the field of electric bound charges, and the next thing is the electric displacement. Okay, so and that's kind of the one of the goals of the chapter 4. Okay, so here what we're going to look at is this. We put the dielectric material inside the electric field. We get this sort of polarization, and now the question is, what is the electric field that you're going to get inside the material? Okay. So with the electric displacement, we're going to address that question. Okay, so here we're going to jump into what actual electric field we have. Okay, so polarization is one issue, but electric field is the actual question we had. What kind of electric field we get inside the material? Sounds good? Again, any question on this? Yeah, I tried to make the video available today. Okay, so for the next topic, let me start by one example. Okay, I'm going to ask the question and I'm going to go through the definitions, and then we're going to come back to the example. Okay, so imagine one case like this. You have a charged sphere, okay, that is carrying the total charge of Q. Okay, you have done that many times before. You know that the electric field created by this at distance r is very similar to the electric field created by a point charge. So E dot r is 1 over 4 pi epsilon 0 Q divided by r square times r hat. Okay, so you know what kind of electric field it creates around the sun. Okay, now I want to do this. I want to encapsulate this charged particle inside an insulator. Okay, So imagine what you do is that you cover this by a plastic. Okay, so it's very asymmetric. Let's fix this one. Okay, so now what is the electric field here? Okay, what is the electric field at this point? What is the electric field right here in the middle of this dielectric material? Okay, so here is question. Okay, so I can tell you qualitatively what's happening, and then we're going to formulate certain things, and by the end of this section, we can actually calculate the electric field. So what's happening is that imagine this charge is positive, okay? What it does is that if you look outside right here, the effect of the dielectric just disappears. Okay, so if you look at outside, this dielectric is not going to affect anything, and we can use the Gauss law and calculate electric field the way it is. Okay, so this is outside. Inside, what we have is this. We have electric field, we also have polarization as well. Okay, so this positive charge creates an electric field that is going to polarize everything here as well. Okay, so the electric field we get inside is a result of the polarization, okay, polarization of the material, and is as well as the result of the electric field created by this, okay? And because of that, we're gonna get some electric field that is same direction most likely, but different strengths inside the material. And once we come outside this, the effect of this dielectric material is going to disappear. Okay, so this is the kind of thing we're going to calculate in this section. Okay, so let's go step by step, and we're going to look at how we can calculate electric field here, which is actually a result of two things: the actual electric field created by the positive charge and the electric field created by the polarization. Okay, so keep that in mind. What kind of electric field we have inside is a result of two things: the electric field that would have been there if there was no dielectric, plus the electric field created by the polarization. Okay, so hang on to that, and I'm going to provide some definitions and formulate some basic stuff, and then we're going to come back to such problems. Okay, so again, we have first some electric field, and then we have some polarization. So these two things that we have. Okay, electric field is created by charge density, let's say rho, okay, by charge distribution. And then polarization, we said that depending on what type we have, we can always assign volume charge and surface charge. Okay, so polarization itself can create some charge distribution. We call that bound charge distribution, and that is negative of polarization P. Okay, so the relationship between electric field and rho is through the Gauss law. So divergence of E is rho. Okay. And if we have polarization, we have some charge density created by the polarization as well. Okay, so I define this charge as the total charge here. Okay, by the way, I need epsilon 0 here as well. The divergence of E times epsilon 0 is rho total. That I'm going to break it into two parts. One of them is the free charge distribution, which is the actual charge that you put into the problem, like the Q here. Okay, so this is the free charge, is the actual charge distribution that you put in, and then add the component rho B, that is the charge density created by the polarized object. Okay, so The divergence of electric field is affected by both of these, okay? And that I can write in terms of rho F minus divergence of P, okay? So rho F free charge is typically the charge density that the problem gives you. It tells you that we have this charge distribution, surface charge distribution, or volume charge, okay? But rho B is something that is created by the polarization, okay? So this is obvious, this is hidden in terms of how you want to think about what is rho F and what is rho B, okay? Rho B is hidden in dielectric material, but rho F is the obvious one, okay? So if we look at this, now we have epsilon 0 E here, and we have these two terms here, okay? I can put this back, okay, and define something like this. Epsilon 0 times divergence of E plus divergence of P is rho F, okay? And this form of the equation is a lot more helpful than we have on the top, because here we have rho F, that is usually obvious what we have, okay? This part, divergence of P is not always obvious. And with this format, because I have two terms, both of them has divergence, I can combine them into one single divergence, okay? And that is divergence of epsilon 0 E plus P is equal to rho F, okay? And that is very interesting and nice, because I have divergence of a vector equal to my charge distribution, okay? And what I want to do is that I want to give this thing a new definition. I'm gonna call it D, okay? And that is called D electric displacement, okay? And this is very useful because it's basically telling us that the divergence of D is rho F, okay? And this is very similar to the Gauss law. This is, in fact, the Gauss law in the presence of the dielectric, okay? If we look at this vector D, this is similar to electric field, okay? Because it's epsilon 0 times E, but it includes the polarization as well, and the polarization is the hidden part of the equation that creates electric field as well, and a lot of times we don't know what P should be, okay? But with this one, we can directly go from the obvious charge distribution and calculate D, okay? And when I do a couple of examples, you will see why D is very useful, okay? And this is the differential form. If you look at the integral form, this is interchangeable. We can say d dot dA over a closed surface is equal to Q free enclosed, okay? So hold on to this, and this is gonna be always our starting point to calculate electric field when we have dielectric material, okay? Again, I'm gonna remind you, inside the dielectric material, the field, the electric field is a result of two contributions. The free charge, which is the Q that we have here, and the polarization, which is P here. P itself is usually unknown, okay? So you will find yourself trying to calculate E from two components. One of them is known, the other one is unknown. So that's gonna be just a source of confusion. But if we look at directly at the electric displacement, okay, which is only proportional to the free charge density, we can easily calculate electric field here, okay? We can calculate D here, and from D, there are steps that you can take and calculate electric field, okay? So let me just focus on this example again, and instead of electric field E, let's calculate D. And then you will see calculating D in the presence of the dielectric is as easy as calculating electric field in the absence of the dielectric, and that's why it's useful. Okay, so let's forget about electric field and let's focus on D. Again, I'm going to remind you, whenever you have dielectric material, okay, trying to calculate electric field, the way you do that, you find the electric displacement, which has very similar characteristic to electric field, with the difference that it includes P as well. Okay, so it includes one of the unknowns in the problem. Okay, so for such kind of geometry, if we look at D, we can actually look at the integral form. Okay, D is going to be uniform. If Q is positive, D is going to be always a vector pointing outside. Okay, so this is D here, this is D here. Perhaps if we go further, D becomes smaller. But if we look at the integral form of that, the integral of D dot dA is going to be D times 4 pi r square, and r is basically how far you are from the center of the sphere. So this is the integral of D dot dA, and then the free charge enclosed here is going to be always the Q that we have in the middle, on the sphere in the middle. Okay. Of course, if you look at this dielectric material here, there are some bound charges as well. There's going to be polarization as well. We don't know what is that polarization yet. We don't know what are those bound charges yet. But here we don't need to care about that. If we want to look at the electric displacement, we only look at the free charge, which is the obvious part of the charge distribution in the problem. Okay, so QF is going to be equal to positive Q. Combining these two, we can say D, of course, in the r hat direction is going to be Q divided by 4 pi r square. Okay, and if we use in the terms of the vector, D is this times r hat. All right, so let me rewrite what D is here. You know what? Because I need to do a couple of more lines with that. So combining these two, I can say D is 1 over 4 pi Q over r squared times r hat. Okay. So this is the D that we have. Okay. Now, if you want to look at the electric field inside, D is epsilon 0 times E plus P. We don't have polarization, we don't know what is polarization yet, okay? So we cannot really calculate E at this point inside, okay? But if we look at the outside of the dielectric material, we know that here there's no polarization. We are just in the free space in vacuum here. So there is no P. We can directly relate that E times epsilon 0 is equal to D, which is equal to 4 pi Q over r squared times r hat. Okay. Now, if we divide every single term by epsilon 0, E is D by epsilon 0, and here we get 4 pi epsilon 0 Q over r squared times r. Okay. So we already can show that if we encapsulate the charge, the charge sphere, by a dielectric material, outside the dielectric material, we get electric field that is exactly similar to the case that there was no dielectric. Okay, we can say that for the outside, but for inside, we need to learn a few steps to kind of relate electric electric polarization to E, and then we can calculate it. So at this point, we cannot calculate E inside because we don't know how to relate P to electric field. Okay, so I'm a little out of time. Okay, so I cannot complete that part, but I can give you a little glimpse of what we're gonna do next. Okay, and that's basically relating the electric field and polarization here. Okay, And if we can relate these two, okay, we can correlate one part of the unknown to the other part, and we can calculate electric field inside, okay? And we cannot do that for any type of material and for any type of electric field. If they are too strong, we cannot really do that. But for a lot of materials, what happens is that the electric polarization is actually proportional to the electric field, okay? That means if there's no electric field, there's no polarization. As you increase the electric field slowly, you get a polarization that in terms of the magnitude and strength and also direction is proportional to the electric field, okay? If you make that polarization proportional to the electric field, then from the D, you can calculate both electric field and polarization as well, okay? So that's what I'm gonna do on next Tuesday, okay? So I'm gonna set up certain equations how, by the way, those materials are called linear dielectrics, okay? I want to present how linear dielectrics get polarization proportional to the electric field, and we're gonna do a couple of examples like this, where we have, we put charge distribution somewhere. In this case, it's center of a sphere. Other cases, you can have cylindrical symmetry. And that creates electric field. Electric field polarizes the material, and the polarization in other way affects the strength of the electric field as well. Okay, sounds good? Okay.
Sounds good.
So I got the feeling that the discussion on the polarization and how that can be related to surface charge was I guess it was confusing. I did not get any question on that. What I very strongly suggest to you is that before the next class, watch my class again, okay? Ideally, read the textbook again. And this is one of those conceptual things. It's not mathematically heavy. It's pretty much conceptual, that if you get it, then you get it and you will remember it for the rest of your life, okay? So please do that before coming to the next class and ask questions.
Okay.
Sounds good? So technically the dielectric is an insulator. Yes, that's a different name, but we are more used to calling them dielectric. Yes, these are insulators. They don't have free electrons. They do have electrons and protons, but they are bound to each other. They don't move. And when you put them inside an electric field, instead of being able to move any charge, you can just rotate them and polarize them in one direction or other. Great. Okay, you guys enjoy the rest of your day. Please read the textbook and watch this video again before coming to class next Tuesday. Other than that, enjoy your Thanksgiving break, and I will grade your midterms. Hopefully, you're gonna get something that makes you happy.
Thanks,
Thank you,
Professor.
Professor. Have a good day.
Thank you. See you guys next week.